Okay. We're going to start with a demo and see if we can wake up. We're going to show a demo of a very simple application for note-taking, which is deployed in a Kubernetes. And it is deployed by default. So you have an option for note-taking. You can install C notes. We can do a test here. So this application has a couple of problems. One of the things it does is that it saves the directory where the notes are saved within a container. And if we ask here for the list of the notes, what we do is a list of this directory -tc. And in the same way, if we're looking for a file that we might be interested in, for instance, resort.com, we change again to /tc, and here we can see the resort.com of the file that's in the container. Okay, so here we can see information. This is a problem because we shouldn't be able to see information that we shouldn't see, but that's not all. If we, for instance, if we have some notes and we type here result.com, and then a server from a malicious company, let's say 8.8 or 8.8, I don't know whose server is that, so we can type that result.com, so any request goes through that server, and we change the TC again, and we create it, and we go back to our list, and we see the content of that file. So we change this again, and we can see that we have overwritten the content of that file, and we can, in this way, overwrite any system file. Another problem that we have here and that we have identified, and this is something typical in Kubernetes containers, and that is that Kubernetes by default, it has a token of a service account. If I change the path here of this cookie and I say that I want to see the token file of that directory, we can see that we have access to this token, and we will see later on what we can use that token for and where it comes from. But that's a different problem. So the problem is not only that you can see the token, but also that Kubernetes has a token always in a specific path. So if you're doing an audit to an application in Kubernetes, if you have a vulnerability of this sort regarding this path, if the application is deployed in Kubernetes, you can see it by accessing this token. And by default, that is the case. And the developer also has forgotten to disable sort of a cleanup point for tests, perhaps, that allows to transfer parameters to the ls command that, for instance, gives us the listing of the current directory. As you all know, with Linux, you can concatenate commands. So the semicolon is codified as a percentage in 3b, and the user running the container. And in this way, we can actually make requests. I have my notes here for the presentation. So I could make a request to external services, for instance. In this case, we're going to download the web page of Lugo, for instance. And so the page is now being downloaded. Sorry, I've forgotten the sign here. There it is. So the page is downloaded, and if we go to notes, this is the content of the page, this page in the index. So in this way you can download payloads or to establish some time of persistence, or you can communicate through the network. We could do a lateral movement if the container is compromised. Okay, so let's move on to the presentation itself. What we're going to talk about today is how we can strengthen or fortify the deployment of applications in Kubernetes. In the demo that you have seen, it is deployed in Kubernetes with the default parameters, and we're going to give you some information, very simple information that you can use in your deployments. And at the end, we will see how, by using exactly the same application without changing a single code line, how we can deploy that application. And fortifying or strengthening containers is not the way to fix vulnerabilities in your application. That is, if somebody says you have a vulnerability of a remote command execution, and then you say, I'm going to deploy the application in such a way so that you cannot do that, and I solve the problem. No, the problem should be solved in the code. This is just a plan B, so that your plan B, so that your application is not compromised. Okay, my name is Rafael Troncoso. I work in United States in the sub company, and I'm part of the security champion in that company. I write nowadays. I write more on Chema's blog, and I have published a couple of books with Fran and also with Elia. And that's my CV, really. And I give the mic back to the boss. You've left out the main thing, that you come from Cádiz, and so do I, even if you can't hear it in my talk. I am a proud member of the team Crazy Ideas in Telefónica. And with Rafa, we have this common blog. I'm also into security, and I have also published a couple of books with Rafa. But let me tell you that I am very excited to make this presentation jointly with Rafa, because it's the first time that happens, and in the Rooted conference, that's great. So let's begin. First of all, disclaimer, everything we say here is we are responsible for, and it's completely independent from the companies we work for. You all know that during the deployment of an application, the base image is a fundamental part. And that image is within a cycle which is called the supply chain. And that's the first step to fortify or to harden. And that image has to have gone through certain, needs to meet certain requirements. It has to come from a reliable source. It should have been scanned to see if there's any nice surprise inside. And finally, small images. This is not about reliability of our functioning. So, because that's actually indifferent. What we are after is for the image to have the minimum possible number of tools. And why do we do that? Because should your container be compromised, you are then not allowing that person to be able to do the same mess within the container. So you do not leave tools there for somebody to do exploits, lateral movements, or whatever. You have to leave the minimum possible available tools. And which is the best way to do that? We will do that later on in more detail, but for that we will use what we call distrolex, which is to distributions. These are images that do not even have a shell. So imagine how complex it is for an attacker. Without a shell, what do you do? There are many MacGyvers that you can download a file like a quiz, but at this particular point, there's no shell. There aren't even packets to install. So that makes it complex when it comes to your deploying the application, but it's worth it because of how much it hardens the application. And then there is Alpine, or which we use a lot, and we're going to try to avoid using that one, because Alpine is actually a full operating system. So what you're seeing there is the Docker file of the demo that Rafa has shown. And it's a very typical Docker file of what we tend to see. There's the multi-phase, it's made in the Go language, the application, and I think this is something we all do when you launch a container or an application. This is a typical Docker file with its Alpine, so it's all pretty standard, really. And look at this other one. This is the one we shall use in the final demo. If you look at this one, it has more lines because we've made some operations for the hardening of these containers. The first one, when we launch the application, is to generate a user and a group of users. And why? Because that user and that group are going to be the ones that execute the application, because you know that in Docker, if you have an application in Docker, it's in a root mode, in an administrator mode, and be particularly careful with services which are more critical. So that's the first one user, one group. And this is the distroless. We will not use Alpine, but we would go directly to a distroless distribution that has just the minimum stuff, which is it's a very basic operative. And it's so basic and initially so difficult to handle that we can't even easily deploy the application because we do not have tools. We have to do it with the Docker file. With this command, we send the application, and by using the command and the parameter show, we give the permissions to the users and to the previously created group in the Docker file. And that way, we make sure that the application will be executed within that frame of one user, one group. Okay, so finally you can see here that we allocate the user that's going to be using the application, but we do not name the user, but rather the ID, and we will tell you later on why. And finally, you've seen the 88 spot, yeah? We're going to talk about the security concept. Many of these concepts are derived from Docker. As you know, Docker is the better known containers engine, but there are other options. And in this case, we will talk about what Kubernetes offers, which is very much derived from Docker. And we will talk about these different items in the next slides. But before that, let's talk about how access control works in Kubernetes. There are three phases when we do a request. For just to remind you, Kubernetes is nothing but an API with a database behind, but it stores everything in a couple components, a scheduler, a queue layer, and what we do is we make request to the API, and for that we can ask Kubernetes, I want to set up a pod in the team 1, and this pod I'm going to run it by default because we've said that by default things run as a root. So when we make that request, the first thing Kubernetes does is to authenticate our credentials. It verifies whether the credentials we're sending are valid, and if they are valid, then we move on, and otherwise we don't. Second phase, authorization. Can this user do this to generate a pod in the namespace 1, etc. And the third phase is what we call the admission control. And there are different types. There's one called post-security policy. which are policies that you can deploy at the cluster level, where you can define, or you can tell Kubernetes, I want in this to have in this Kubernetes no pods that run as root or with privileges, etc. So a normal user wants to generate a pod that runs as a root, then that won't happen. The admission controller would deny that request. Okay, so these are the three phases in which Kubernetes allows you or prevents you from doing things in the cluster. So the first thing we'll see is the privilege mode. Basically, privilege mode allows you, when you're running a container, that container are Linux processes, basically, that are restricted because they have the namespace restriction and the syntax, which are Linux features. So in privilege mode, that container, that process, has the same permissions that any other running in the host, and that allows you to access the file system of the host. And that's very dangerous, because you could even change files of the files system or interact with certain elements. So running in this privilege mode would allow you to do that. And in Kubernetes, any file that you're running is by default in non-privilege mode. But this is a feature that can be changed. And nowadays, you can get a cluster where the by default privilege mode is false, but you can tomorrow have another cluster in which that's not the case. So to avoid problems, you can simplify this line on the red square where you so that the files run on a non-privileged mode. Then we have the concept of running the container as non-root. We've seen already in the Docker file that we have improved and where the user ID. And if you run a container based on that image, that container is going to run with that user. But in companies, particularly large companies, you often have equipment busy with the maintenance of those images. The no-went image concept, there are companies that have to follow regulation because they work with government, and the images need to have a specific configurations to meet all of those requirements. And so there is a separate equipment that maintains those images, and if somebody makes the mistake and removes a user or modifies it, and we wouldn't have control. So Kubernetes offers us two checkpoints, two ways in which we can make sure that the pod doesn't run as root. The first one is run as non-root. So when you try to run a pod, Kubernetes looks for the image in the container, and it sees whether the user command has been defined. And if it has been defined with a value above 0, because 0 is root. So if the file is not in the image or it is defined as 0 as root, Kubernetes would deny the setting up of that pod and would generate an error message. And what happens here? If somebody makes a mistake and specifies user rather than the user 1000, the user 10,000. If you run the container with that image, what happens is what you can see in this image here. You can see it here. This is what happens. Kubernetes honors the ID 10,000 specified, and the process runs as such. But because that user doesn't exist in the image, what happens with that group? Well, it sends or turns it into a root group. So you're running a process which is not root, but could have privilege or be able to do things that it shouldn't be able to. So that's one of the options. And the second option is you specify in your deployment the user ID and the group ID. And here you don't have to specify both. You can identify just the ID of the user. But as you can see here, if you specify only the user ID, then you would have the same problem that we have had before. If we have an ID of a user that doesn't exist, then that container will end up running as that user, but belonging to the root group. So what we recommend is that when you define your application, you should define both the user ID and the group ID. And if for any reason the user and or the group do not exist, then Kubernetes will honor those values and will run your process as that ID, that user, and that group. And in worst case, the application will have permission problems. But for me, that is better rather than the application running with a false sense of security that my application is running as not root, when it actually is running as root. There's something else which we call the privileges scaling. A good practice when we generate Docker images is to delete all of the files that have the set UID, and Kubernetes allows you to specify it with that feature, allow privilege escalation to not to allow it to acquire new privileges. And in this way, you could execute, but you would not escalate privileges. And this is a good practice that's available there. With just a single line in your deployment, you can save a lot of headaches. Something else we have seen in the first demo is that we could overwrite the file, the resolve.com file. And you could overwrite any file because it was root, and the file system is as reading writing set up. So we can ask Kubernetes to set up the files system within the pod as just reading. So I can modify, I can identify whether my application has a vulnerability that allows you to write in this file system. But sometimes we need, like in the application we have just seen, the nodes are written in a directory in the file system, or we need to set up a temporary file, some log or whatever. And if we need that, we just need to define a volume, like we can see here, and to set up that volume in the directory where you need to be able to write files. And remember that when you write within a container, once the container dies, everything that's inside dies as well. So immutability is very important. But if you have to write temporary stuff, then you set up a volume there. But you have to specify that you should be able to write in the file system. It's very simple, but very powerful. And finally, I want to talk about capabilities, which is a part of Linux, which it's a functionality that allows you to define in a very granular way the permissions. In the past, the processes would run in the privileged or non-privileged mode, and that was it. But as the system has evolved, the core has requested more granularity for permits or permissions. So when you erect a container, these containers inherit a number of capabilities from Linux. And then there are other lists, another list that's not inherited, but it's available. And it's important to apply the principle of less privilege principle. And what we do with that, we have the capabilities drop option and the capabilities add. So in the first one to the left, we're telling Kubernetes, remove all of the permissions from this file. And in the screenshot below, you can see here, I am running the container as root. And I've tried to do a ping to my local root. I am root. I tried to do a ping, and it's denied because I've removed all capabilities, all permissions from there. So if you need to be able to do ping within your application for whatever reason, okay, you come to this side and you say remove all capabilities, add only the one that allows me to do ping, or in this case to send network packets running in that very container, but now with the ability to send net packets, we see how the root allows to do ping in this way.
Again, this is very strong. It gives you more control about the process that you can run or not. And the recommendation is that you remove all the capabilities and then you start adding those that you need. Let's continue with pods, and we continue with service accounts. This is very important. Each pod has in a Kubernetes cluster has associated a service account. This service account, if you don't associate that to a specific one, it's assigned to a default account. So that account could be used to contact and communicate with the Kubernetes cluster using as credentials a token. Rafa did it in the demo at the beginning, how he filtered that token. Below you can see the cord command line, and using that profile for the exploitation. 95% of the applications deployed in a Kubernetes don't need to communicate at all with the cluster. So we should disconnect that, as you can see below. Let's see if it works in that line over there. Connection with this, we're going to talk about networks, because communication between pods, among pods, it's quite tricky. It's complicated. There are 4 problems regarding communication. You can see that in Kubernetes communication, from container to container, from pod to pod, which is the one we're going to discuss now, the service to pod, and to external service to the service, external server to the service. What happens here? Pods are completely visible among each other. There's nothing in between. What IPs use to communicate, even if they have to access to consult the database used by the internal the cluster internally, it's open. So we have to manage that somehow. You cannot leave that open communication in case we have the problem that we already mentioned with the token. So from the spots that you have there, the interesting one is the last one. That's what I just said. All pods by default can communicate among each other. And how do we do it? Because it's not easy. Kubernetes doesn't let you a direct way to manage that kind of communication, and we want to do it. We don't want to leave that open. So we have to use plannings, and that's not easy. Not all pods allowed to apply those network policies, but others do. So you have to see, depending on your deployment or infrastructure, which is the one that you are interested in using. Okay, the CNI doesn't need to do with anything that's out, anyone who's outside. So we're going to talk about network policies in Kubernetes. It's a very simple concept, but it's very strong. It's not a firewall, but it allows us to control the communication from the entry communication, exit communication for pods. In Kubernetes, by default, all pods are in an internal network and all can communicate among each other. If I deploy a pod in Kubernetes, I can send requests or communicate to the pods that are in the system, in the space that they are existing, and do things. I could just break down the database or if there's a vulnerability, I could exploit it, and we would have a problem. So Kubernetes offers these network policies. They belong to a space name, and as many other things in Kubernetes, use tag selectors. Everything is based on tag selectors. Not all plugins, DNA plugins that we have seen in the previous slide, support these network policies. So by default, in Kubernetes, network policies don't exist at the level of the cluster. They are all at the level of the space level. And there are some applications there's plugins like Calico, like CNI. They have these policies at the level of This is the global network policy as it's called, but that's an extension through the CNI plugins, and that's nothing that is not included in Kubernetes by default. This is an example of a network policy, the same file cut in 3 pieces, but it's a whole file. In the description here on the left, if it works, the one on the left starts with the typical file that we could see in Kubernetes within the name, metadata, but we specify the pod selector. What we say that which pod will be affected by this network policy, and as you can see, it's based on tags. If you have a pod in the space name that has this tag, in this case RoadDB, all those containing this tag are affected by this policy, and then we explain which network policies. Ingress is entry traffic, and egress is exiting traffic. In the middle screenshot, we have the specifications for ingress and how we're going to control that entry. There are 2 ways of selecting or choosing the traffic. You can define traffic, the entry traffic, through IP blocks, as you can see with CIDR, and you can even add exceptions to that IP block, but that won't affect to that specific subgroup. We can also define the traffic defined on space tag and space tags. Every pod deployed with this tag will be allowed to connect with me. So lastly, you can be more specific, and you can say that I want that this pod having this tag is the one that can communicate with me. As you can see, each definition, IP block and a namespace selector, have a dash. That means or. That is, I'm accepting, in this case, traffic from that IP block, or pods which come from the space defined, or pods which are defined based on that tag. If we want to do an AND, we remove the dash. If we remove dash to the space selector name, I will accept only traffic from that IP block, and besides, belonging to that space name. And if we don't remove the dash, it would be or from the pods that have that tag. The work is defining which protocols and ports do you want to limit. In this case, so it only affects to the port 6379. Then we have the egress, the exit traffic, where I can communicate. In the example, I just have defined an IP block and a protocol and a port, but as we can do with ingress, we could specify tags, space names. You can use that too in egress pod too. Good practices in this field. Again, in Kubernetes, a pod network is open and you can communicate with everyone. So we recommend to implement a policy in this space name that denies the whole traffic, both entry traffic and exit traffic. What does it mean? If you deploy a pod in that space name, you can even communicate to that pod. The idea is that you deploy this policy and then you start opening whatever you need. It's the same as before, the principle of less privilege. You start blocking everything and then you start opening the connections that you need. What you can see there, it's everything that Rafa has told applied directly to our hardening. Everything that you see in the right-hand file is what Rafa has been telling to fortify, to strengthen all the parameters that we have just mentioned. This part here, just to achieve, I think, Rafa, this is yours, excuse me. Well, 30 minutes ago, more or less, I'm just checking the watch. The first demo that we did, we showed how we could see the content of a file from the system and how could we could see the content of the directory, the files, and how we could overwrite the files, and how we could run remote commands to download things within the container. So we're going to run the second demo, and it's exactly the same application, but based and deployed with the right-hand part. All the settings that we see on the right-hand side of the screen. So we're going to make the second demo. This is the first demo. This is the second demo. It hasn't changed at all. I can here create my notes as we did before. Test. Just I go to my list. I see that I have this note V2, and I can open my notes. What happens if we try to list the list of the new -etc? In this case, we should be able to do it because I'm running the user I'm running now. I have the ability to list that directory. The vulnerability exists. We haven't fixed vulnerability. As I said, vulnerability has to be fixed in the code. This is plan B when your application has been compromised. But if we try to do what we did before, which is overriding resolve.conf file, we can put here whatever. So we change the directory to etc. If we do this now, what happens is that we will be displayed an error. The error, I can show you the logs. As you can see, we have the log for the container, and the error displayed is because I can open the file for writing because the file is assembled as read-only mode. Once deploying the application with that read-only mode deployment, there we are protecting ourselves in case someone compromises the application, so that person cannot create persistencies because he cannot write in the system, he cannot modify any container. Another thing that we have seen before was this exfiltrating the token from the service account associated to the pod. As Fran explained before, that token can be used to connect to Kubernetes. If it's true that Kubernetes by default, when you create a service account, the service account doesn't have any permission, any privilege, but people do things. I have a friend who created this service account in the administration group by default, so all the pods that were running with that token, potentially, if that token was exfiltrated, he could have access to the cluster. And a friend of mine actually, if we try to access that token again, we change the path, we put token, we have another error because it says that the file doesn't exist anymore. Kubernetes, we said that to all Kubernetes, do not create the token. If you don't need it, don't establish it, because there's a credential that gives you access to the cluster. So if you don't need it, don't use it. And if you don't establish that, you cannot exfiltrate it. So as we said that it couldn't create it, we have one problem less. And the problem that we saw before is the possibility of running remote commands through the debug. If we try to do this now again, nothing happens. In this case, we see that there's no difference here, and if we see the logs from the system, what it says here is sh no such file, so I cannot run anything. So this is very strong. Running a distribution or an image in which there's nothing, if you don't have tools, it's very complicated for an attacker to compromise a container or to do things. So that's the other thing. And finally, I'm going to show you, I'm going to back to the initial application because we have removed it in the option of running things. I'm going to do again. We saw before that I was able to download the file, the Google web page. So we're going back here. Let's do something here. Let's change output to output 2 to show that it still works. It works. the command the wget command has been run, and it works. And we're going to apply the network policy I mentioned before. The first policy that I'm going to apply is the one that denies all traffic. What happens when you do this? When we do this, what happens if we try to do something here, for instance, create nodes, as you can see, this keeps thinking, it's trying to do something, but it's nothing to be done because we cannot communicate. We just cut the communications, all the entry and exit traffic from the pods with that path. This is not obviously what we want. If you deploy something in Kubernetes, you want to interact with it with service. So what we're going to do now is to deploy a new network policy. They add to each other, policies add to each other, and the more permissive one is the one who wins, which wins. I don't want the order to be relevant. I want to deny all traffic, all entry traffic, and then I apply another traffic that I want to accept entry traffic from a certain IP or a certain pod or whatever. That's added, that's stacked, and the most permissive one wins. So if we apply the second network policy that allows me, and I will show the content, we're going to deny now is the outbound traffic. So now if I connect again, the application works again. But what happens if we try again to download the Google web page, or we try to download a payload or whatever? That's the same. It's stay blocked, thinking, and when after 20 seconds something, you would have this error, bad address. It's saying that it can communicate. As we have seen there, we're going back to the presentation. As you can see, applying certain settings or configuration values in the deployment of Kubernetes, we haven't fixed anything. The application is has the same vulnerabilities. But what we do is to contain the attacker within the container. So the idea is to not let him do lateral movements that do not create persistence, that he cannot do anything. That doesn't fix or doesn't help with SQL injection problems. When you're going to with a database and you have a SQL injection problem, you can exfiltrate data through the SQL injection. It doesn't help with security problems in the part of the client, like scripting and that kind of things. But it's very important to understand that Kubernetes and Docker, by default, sacrifice, let's say, safety in favor of easy of use, user friendly, let's say. So the idea that we have here, to conclude, is that you ask yourself this question. Normally, especially when you are doing the threat modeling to your service, what happens if your application is compromised? What happens if this happens? What? The idea is not the if. It's the idea is to remove that conditional part and ask ourselves what is going to happen when your application has been compromised. I don't know who said the phrase. There are two types of companies: those that have been compromised, and those who don't know, which don't know that have been compromised. Assume that your application will be compromised at a certain point, and what you are going to do or what will you do so that don't happen again. So that's it. There you have the URL of the GitHub. You can find the demo on the folder level files and the components, and we have been faster than usual. The URL is not public yet. Give us 20 minutes, and when we exit here, we will upload the slides to the same repository, and we will make it public so you can download. You will have the slides, you will have the code of the application that we have shown, which is written in Go, and all Kubernetes files and everything. And that's it. Thank you very much. Let's start with some questions. Good morning. I have a few questions, so I'm going to ask you a question until you stop me. Omar will stop you. Okay. Then I will talk to them. Distroless is from scratch. Distroless versus from scratch. From scratching. Distroless, what it does is from scratching you have nothing. Distroless provides you the LIC library, which allows you to run things. In this case, it's a binary written in Go, so it's a LIC file. There's also the base distroless and the static distroless. The base one provides SSL libraries in case you create communications in SSL, and certified downloads the certification, the usual CR certifications, certification authorities. And don't recommend from scratch and introducing what you need in your binary and having the control of what you actually put in. You can download the LIC and play to distroless, or distroless can do it for you. It depends. Also, distroless has a tag. You have the tag. There's a version, debug version, which adds a shell in case you are programming and you need to connect to the distroless. You use the tag debug and you can connect through the shell to see things within. I continue if nobody asks anything else. I've seen that the Docker file you hide the bind false, the shell on bin false. Why do you need it if there's no need of shell? Well, you could remove that. Yeah, there's no need to put that. That's true. He even has a list. We will be around all the day. So just a point, just a clarification. Rafael, security champion SAP. So I'm going to, as Homer Simpson is doing, I will leave, and everything's for you. Okay. I usually introduce in the scheduling and resource requests. I'll put limits to CPU and RAM. I don't know if to put limits to DOS. I don't know if you mentioned those are recommendations, good practices to limit the CPU use and memory. But in this case, we have focused on the approach. You can create a dog in a certain point. But at the moment of hardening the weaknesses from how can we contain that someone compromises your application and containing the attacker so he cannot create persistencies, lateral movements, but defining the resources by default, it should be in the quotas of your cluster from the space names and that you have defined. You have to define the resource, but it's recommended to do it manually. Yeah, it's better to define it by yourself, yes. AppMore and SEPCOM. It depends on what you are running. I haven't started looking at it. I wanted to introduce policies to which calls to the kernel it has. It depends if you are running on Debian distributions or in distroless. I don't know. I haven't checked that in a distroless because there's no package system. Is it actually a definition of the Jammer specification that you go to the kernel? So I think, I'm not sure because I haven't touched that yet, that has nothing to do with the image you're running, but with the calls that you make from the container to your kernel, to your actual kernel. Okay, thank you very much. Thank you very much.